The purpose of the optimization then is to give you an idea of how many iterations that it's going to take to complete a full design, that all of our considerations, everything that we're going through to meet the specifications, the load, the temperature, the environmental variables, all have to play a part in this choice. So this is another situation where I can utilize the configurations. I want to see what my other arms look like. I can use the pin components, but I want to go back and fill these in with the modified arms. So we'll give it a name, and again, these names don't have to stick until we carry further on, because of the associativity, the other things going on. We don't really want to get too carried away and commit as we go to other levels. So just be aware that at some point we're going to have to revisit those and make a final decision as to the naming conventions. All right, so I'm going to reorder, put the pins with the pins, and so I can come over to add to new folder, and this will become my my default, or my crank configuration. Alright, so I'm just trying to organize this a little bit so that when I suppress, unsuppress, or go into those configurations, right now it's participating in the arm, but not in the default. So when I bring in the arm component, we'll drag that in, its location is okay, and we're going to make it concentric. Alright, I'm going to line up to, so let's see, when that rotates over, that should be that inside face. Those become coincident, and face to face, coincident. So at this point there is nothing, I don't have a key in there to start with, but there's nothing really. If this was a press fit, press fits have limitations. Even if it's a light press and we put some kind of retainer on it, a washer with a screw, or a flathead with a custom washer, it's one more part to manufacture, but we're not completely relying on the press fit. This square stock's gonna help quite a bit, but if we get enough thermal expansion that it can, and possibly dissimilar metals, we could see that arm starts to slip. All right, so let's see, fully defined. What is causing that to be fully defined? All right, so let's go back to the drive pin, and we'll look at our mates. Concentric. Okay, those are the three. Coincident, concentric. All right, so now in this case we want this to rotate. We still have to make the allowance if we're going to go with the flange, or if we're going to say that these metals will not cause galling and can actually have physical contact with a certain amount of lubrication, and not have a reasonable life cycle before it tears it up. So unlock the rotation, and I don't know that we can do that per configuration, but we'll give it a shot. Alright, so again, we had to make a decision on each of these joints. Is it going to be the press side or the rotating side? We have to have that clearance for it to be able to move. Alright, so control and drag, and I let go too soon, so control, let go of the mouse, let go of the control. It asks me which one I want, and this is going to be the 160mm follower. So advantage of, maybe it wasn't that one. Alright, so let's go back to 50mm on that one, and we will right click on that one on the second and make that the 160mm follower. Alright, so I need to zoom up where I can see the bore, see the shaft. Okay, and then, alright, so I think on the other one I picked the faces. A lot of times I'll do the contact faces, alright, because we have that working envelope when we get over to dimensioning and tolerancing, that when those two are pressed together, that when those two faces are pressed together, it's going to tell me how much clearance, how much interference I would have if I put a washer, if I put a button head or a flathead screw on the outside of that. Alright, so, well, I guess I didn't. So while we're here, let's go ahead and finish that one out. We'll go face to face as contact. And we'll see which one moves here. Alright, so we can build those out. Alright, so again, just the middle mouse wheel, kind of halfway zoom. And then I need one more of the arms. So we're going to get out of the mate, accept it, hold down the control button, drag in another instance. I'm not getting my combination working there, so if I let go of the control button just a little bit too quick. Okay, so right click, we go up to the configuration selection, change it to the 80 millimeter. Notice that in the 80 millimeter and in the 160 millimeter it doesn't have. Now if this was driving something back and forth down here as well, we would extend the shaft. This would also need that pin. Since it's just rotating, whatever our material and bearing, sleeves, load is going to manage is going to be acceptable at this point. And every time we go through the process, this process and another iteration, we're going to look at those loads and the necessary requirements to make this mechanical work. Alright, so concentric. Alright, so now we're in that has the same type of movement. We could apply the mates, and if I go into my drawing is still pointed to that other configuration. So my what if are these three arms, and then we want to check. So I'm going to go ahead and just make another add new folder, and this is going to be the arm configuration. Alright, so the test of the configurations is that if I go back to the default, they all came back on, but the advantage of the folder is that I can suppress them and unsuppress them all at the same time. So since it did not create any interferences, same lengths, it didn't try to move anything strangely within the group, mainly the pins being the common overlap. Since it did not interfere, it didn't go over defined. Alright, so the last one would be to lock this back down. We can unsuppress. Alright, so I have my static, doesn't move unexpectedly. I can have a dynamic that has that parallel suppressed and will move accordingly. Alright, so again, with the design for manufacture, these pins are going to be fairly expensive. Having to turn down, create the flange, we're 10 millimeters and 12 millimeters, I believe, 14 millimeters. So we actually have 2 millimeters to turn down on each side in our lathe process. And then this length without taper, really the area between the pin, and this is where we start with the design for manufacture, the dimensioning and tolerancing, and how we're going to manage this geometry. So this integrated flange is a good idea, but it increases the cost of this part. If it's some specialty material, then maybe we do want the flange in there, but at some point we're going to have the conversation of maybe we buy 10 millimeter shaft and this is a washer that we slip over, or or as part of the flange bearing that gets pressed in, and we don't need that geometry. That leaves it to where we just have the clip, we just have the machining of the notch to actuate our drive mechanism. Alright, so some of the things that we can do for tolerance, if this is our 10 millimeter shaft, 394 probably plus nothing minus 1 in a precision shaft. It depends on what we order, but one of the things we can do is start to look at our material conditions. So if this was set up to receive the flange, then we would probably make it a little bit smaller so that it is an interference press fit. We want it to be a nice tight fit for that sleeve or that flange to hold on tight. If this is the clearance material, then maybe the shaft goes 1/1000th undersize, and we want these holes to go 1/1000th oversize if this is going to be the rotating load-bearing face. So here we can go over to direct editing, and direct editing is handy in that it does not change the identity of the face or the address of the face as far as SOLIDWORKS is concerned. So if I grab that face, see if I can do both of them, but hold down the control button, and if I say move face, 10 millimeters, well, it's pretty much going to close it up, so that's not going to help us any. So 1 millimeter, and you can kind of see in the yellow that it's making the hole quite a bit smaller. For clearance, I want it to be a little bit bigger. So always have to do my math. If 40 thousandths, roughly 40 thousandths is 1 millimeter, then 0.1 millimeters would be 4 thousandths. And so I want to be about 0.2 millimeters bigger, about 8 thousandths. Or 8/10ths, so about 1/1000th bigger. 0.0. So that would be 4/10ths of 1/1000th, and 0.02. That's what I said. 0.02 would be about 8/10ths of 1/1000th bigger. All right, we accept that. And now I've put that clearance in there as the low side of the tolerance. I want a minimum of 2/1000th clearance. With my tolerancing, then this could go 1/1000th, even larger. And on the shaft, if it were to go 1/1000th smaller, then we would have a total of 4 thousandths. So an acceptable tolerance for this rotation, 2 to 4 thousandths of an inch. For our functionality is going to be fine. All right, so going through that stack up process is going to be a regular exercise and just running through the logic. Does it make sense? As we refine and build these, then we may find that is too loose or too tight, and have to go back and make those adjustments. So if I go back into the assembly, if I had cut those bigger, well, I did actually lose it. Usually it does not lose its mind on the mates. Okay. Well, then we're going to have to reselect those faces because they came up with a underdefined error. So doesn't happen very often, that it loses that face with the direct editing, but concentric, coincident, yeah, I'm not seeing it. So I'd have to go back in and reselect those faces, or just on the geometry, go in and do the suppression. The other thing is we can design it at a line-to-line interference fit. Right, so it doesn't have any tolerance built into it, but at some point you're going to have to manage the the geometry. So I need my drawing. All right, we open this up. We'll see if it got too crazy. So yeah, it picked something. So can't say that I'm surprised. The default I didn't see my default look that weird, but okay. So that one looks pretty good. That one has the extra geometry. So we make these modifications, if we're making these decisions, then we have to figure it out. So this one went to the 394 plus, and I'm not seeing it. So did it? If we expand out, the move face is there. So yeah, that's about right. 0.03397, so about half of the, yeah, okay. So just kind of looking through the tolerances, those get a little bit bigger and have a little more clearance. All right, so again, this is an iterative process. We're going to check and recheck, and very rarely is the design going to go through in one pass and say, there it is, it's perfect. You know, if it is, it's probably two pieces and we didn't have to think that much about it in the first place. Anytime we accumulate a joint, a rotation, a joint, you know, every one of those is going to have to be scrutinized too, even if it's just a cursory glance and say, yeah, that's going to be okay, or no, we need to look a little bit further into it.